In this video, we provide guidance on how to complete the mini projects associated with the lecture's dynamical systems and bifurcations. The first mini project involves finding equilibrium solutions for the Lorentz 63 model. To do so, we find these steady state or equilibrium solutions by setting dx dt, dy dt, and dz dt equal to 0. We can then start to eliminate variables. For example, in the first equation, we either have a equals 0 or a not equal to 0 and x equal y. We've eliminated one of the variables, and for example, then we could use the third equation to eliminate another variable under some assumption on the parameter c. So the main thing with this project is to keep clear what the assumptions are on the variables as you eliminate and eventually solve a scalar equation for one of the variables and subsequently substitute for the other variable. For the second mini project, we want to determine the stability of the equilibrium solutions we found in the first mini project. So this involves determining the linearization about the steady state solution. So if we think of the linearization as a 3 by 3 matrix J, then the ij element of this is the partial of the ith equation with respect to the jth variable. Another way of seeing this, alternatively, we could calculate the directional derivative. So for a function f that maps R3 to R3, as we have here, we could calculate f prime of x, vector x, so x in this case is x, y, and z, times some vector v as the lim sup, or hopefully the limit, as epsilon goes to 0 of 1 over epsilon f of x plus epsilon v minus f of x. Okay, so this will more than likely involve making a Taylor series expansion, and so again we'll get the Jacobian matrix by letting v equal 1 0 0 0 1 0 0 0 1. So this gets us the 3 columns of the Jacobian J. So J is f prime of x. Okay, subsequently what we need to do after we've calculated J is find eigenvalues of J. The next project involves downloading the files, PredCore files, using them to do continuation, and what should happen when you try these is you'll get stuck where the implicit function theorem is no longer valid. So this is going to correspond to a fold or a saddle node bifurcation. So to see this, try plotting x versus alpha, and hopefully you'll see that you can run up and maybe if you relax the tolerances you can jump over the saddle node, but more likely you'll get stuck near the saddle node bifurcation points. So the next thing is to modify these codes, and basically it's just modifying the PredCore. So copy PredCore over to a new file, call it PredCore new or whatever you would like, and then we're going to modify this in 2 important ways. We're going to change the tangent predictor, okay, so that it's calculated based on the vector in the null space, Notice that this is done using the MATLAB command null. Okay, and then the corrector, since the Jacobian in this case f is no longer square, we're going to use a Gauss-Newton method, so we're going to use the pseudo-inverse instead of the inverse in this determination of the corrector step using the Gauss-Newton. Okay, so let's look a little more specifically at the problem we've been interested in. So in this case, the Jacobian is going to look like it's going to look like 2u1 2u2. So this is a 1 by 2 matrix. Okay, so as long as this matrix is full rank, then the pseudo-inverse is going to exist. So we can use PINV to calculate this pseudo-inverse. Okay, notice that null, the MATLAB command null, returns a vector with v with 2 norm equal to 1. So this means we're finding one of two different vectors. Okay, so the only difference between these two vectors is a multiplication by -1. And if we want to go around the circle, we might have to make the choice of which of these two vectors to employ a little judiciously. So play around with this a little bit and see if you can make make your plot go around and around the circle. We're going to change the way we calculate the tangent predictor using null. We're going to change the way we calculate the corrector by using Gauss-Newton instead of Newton, and we're going to use PINV. Okay, so these are the two commands that you want to employ, and again, this is basically just modifying the existing pred to do this. All right, well, that's it for these lectures and these mini projects. Come to office hours if you still have questions, or talk to your fellow participants. And thank you very much.